Hello everyone, this is a quick tutorial on section 8.1, integral as net change. First, we're going to talk about part 2 of the fundamental theorem of calculus, which says that the definite integral of f of x dx from a to b is the antiderivative, big F of x, evaluated from a to b. So over here is the main statement of the part 2 of the fundamental theorem of calculus. Now, this has many different applications, or it could work in many different contexts. As long as you remember that what's on the right-hand side here is the antiderivative of what's the integrand here. And so here, notice that there are other forms here. So if I have the definite integral of f prime, then that will give me f, because f is the antiderivative of f prime. Okay, another important application, or another context, is right over here. If you take the definite integral of velocity, you should get position, because position is the antiderivative of velocity, and velocity is the derivative of position. And if you do s of t sub 1 minus s of t sub 0, that gives you the change in position, or what we call displacement. Now another application or context is when we know the rate at which people enter a room. So let's say that r of t is the rate at which people enter a room. Well, the definite integral of r of t, which is the rate at which people enter a room, the antiderivative of that would be the number of people in the room. And so let's say that that's a. A of t is the number of people in the room. So the derivative of a is r. Because a stands for the number of people in the room, r is going to be the rate at which people are entering the room. More accurately, it's the rate at which the number of people in the room is changing. Okay, so let's look at this specific definite integral. Here you see that the definite integral of r of t dt from 0 to 8 is equal to a of 8 minus a of 0. This is simply the fundamental theorem of calculus, part 2 of the fundamental theorem of calculus. A is the antiderivative of r is the derivative of a. And what is a of 8 minus a of 0? Well, it's the number of people entering the room in the first 8 minutes. It's the change in the number of people in the room. This is assuming that nobody is leaving the room. We will work on problems later on where there are people leaving the room at a certain rate. But let's say nobody is leaving the room here. And so, another thing to keep in mind is that if we want the number of people in the room at t equals 8, we have to know how many people are in the room initially, because it may not be empty at first, plus the change in the number of people. Therefore, the number of people in the room at t equals 8 is a of 0 plus the definite integral from 0 to 8 of r of t dt. What we're going to do next is look at a very specific example about motion. Okay, so let's look at this example. Here, let v of t equals t squared minus 6t plus 8 be the velocity of a particle moving on the interval 0 to 8, where t is in seconds and v of t is in feet per second. The particle is initially at a position of s equals 3. Part A, when is the particle moving to the left, to the right, and at rest? So let's start by taking the velocity and factoring it. So we have t minus 2 times t minus 4. If we set this equal to 0, then we get the 2 times at which the particle is at rest, because the velocity is 0 at those times. To find out when velocity is positive or when velocity is negative, a handy way of doing it is with a number line. Now, using a number line is not required, but it could be very helpful visually. So if I have v of t on this line and I just test values, I'm going to get positive, negative, positive, which means that the position is moving to the right here, moving to the left there, and moving to the right there. Okay? And so the answer to part A is simple. Moving to the right is from 0 to 2, as well as 4 to 8. Moving to the left is from 2 to 4. And at rest is when t equals 2 and 4. So this is the work for part A. Now part B asks for the displacement of the particle from 0 to 8. And if you refer to the previous screen, the displacement is the change in position, which is going to be s of 8 minus s of 0. Well, the fundamental theorem of calculus, part 2, tells us that s of 8 minus s of 0 is going to be the definite integral from 0 to 8 of the velocity dt. And so what you have to do is you have to evaluate this definite integral of t squared minus 6t plus 8 dt from 0 to 8. Now I'm going to leave the in-between work for you, but if you do it right, so what you should do right now is you should probably pause the video and evaluate this integral, and then restart the video to see if you got it right. Alright, so the answer should be 128 over 3 feet. This means that the particle moved 128 over 3 feet. Next, we want to know the particle's final position at t equals 8. Now I'm running out of room on here, so I'm going to do it in this red box. Now, is that red box or that pink box big enough to do part C? It sure is. To get the final position at t equals 8, or s of 8, we need the initial position, s of 0, plus the change in position, which is the displacement that we just found in part B. And so that would be the integral from 0 to 8 of v of t dt. Well, in the problem, it tells us that the particle is initially at a position of s equals 3, which means that s of 0 is 3. So you have 3 plus, and then the displacement, which we found in part B, is 128 over 3. So all you have to do is do 3 plus 128 over 3, and you will get the final position, which is 137 over 3 feet. Now, the last part, part D, it says to find the total distance traveled by the particle. What this means is that we have to consider when the particle is moving to the left separately from when the particle is moving to the right. And so how do we do that? I am going to erase, actually I'm going to erase. Where's my eraser? Right there. I'm going to erase what I have over here. Is that the eraser? Where's the eraser? Right there. There. Nope. Where's the eraser? Nope, that's the highlighter. Oh, here's the eraser. Nope. Why isn't it erasing? Okay, I'm going to just do that then. Shove that off to the side. Shove that off to the side. Okay. All right. Sorry for wasting your time there. So how do you find the total distance traveled? Well, we found earlier that from 0 to 2, the particle is moving to the right, which means that velocity is positive. From 2 to 4, the particle is moving to the left, which means the velocity is negative. So we're going to have to negate the velocity so that we are anti-differentiating something that's positive, because total distance traveled has to be positive. Movement to the left has to be considered movement to the right in a sense, so that when we anti-differentiate, we get a positive number. Finally, from 4 to 8, the velocity is positive, so we can just use v of t as is. So this is how you do total distance traveled. Now the short way of writing this is 0 to 8 absolute value of v of t dt. This ensures that we're anti-differentiating something that's positive so that we would get a positive result. Okay? So this right here is what you have to anti-differentiate. Okay, and so from 0 to 2, you are anti-differentiating t squared minus 6t plus 8 dt. From 2 to 4, you're anti-differentiating negative t squared plus 6t minus 8. And from 4 to 8, you're anti-differentiating t squared minus 6t plus 8 dt. So what you should do right now is you should pause the video, figure this sum out, and then restart the video to see if you got it right. Okay, so your answer should be 136 over 3 or 45.333 feet. Okay, so now a little graphical interpretation of this. If I were to graph the velocity graph, it would, from 0 to 8, it would look something like this. Okay? This right here is 2, this right here is 4, and this right here is 8. Again, please excuse the scaling here. The point is that velocity is negative from 2 to 4 and positive from 0 to 2 and 4 to 8. Notice that if I were to anti-differentiate, this graph from 2 to 4, I would get negative area because the velocity is negative there. By putting a negative in front of the v of t in this second term, what we're kind of doing is we are reflecting this over the graph and thus having positive area. So this pink part here is negative v of t. So from 0 to 2, we keep v of t the way it is. From 4 to 8, we keep v of t the way it is. But from 2 to 4, we negate v of t so that it reflects over the x-axis so that it becomes positive. So this area that I'm shading in pink is the total distance traveled. The last thing on this video is something that I've been holding out on you guys on, and that is the fact that the calculator can evaluate definite integrals. First, you have to press exit until you see the jump, delete, MAT, and math function keys on the bottom of the screen. Then you select math, which is the F4 function key, and then you select the arrow option, F6, so that you can see the rest of the menu items. Then you select F1, and it's going to be the option that looks like the elongated S. Input the integrand and the upper and lower limits of integration, press execute, and voila! So go ahead and try to replicate my screen right here and see if you get the answer. Make sure you're in radian mode. Homework 8.1 is going to contain some integrals that you cannot do by hand. For those problems, go ahead and use this definite integral feature on the Casio Prism. Bye-bye!